Welcome to our discussion on the critical transition from large language models to truly autonomous agentic systems. This presentation introduces a comprehensive framework for understanding this evolution. We'll explore how 8 integrated capabilities move AI beyond mere linguistic competence. Our goal is to provide a clear roadmap for building responsible and effective autonomous agents. Large language models excel at language, but they lack true agency. This fundamental challenge highlights the gap between linguistic competence and autonomous action. LLMs are reactive prediction engines. They don't retain memory, understand action consequences, or interact purposefully with their environment. This distinction is crucial for understanding the limitations of current AI systems. Building on the idea of this fundamental challenge, we must recognize that simply scaling up LLMs won't bridge the agency gap. While parametric scaling improves linguistic performance, it doesn't create autonomy. True agency demands a fundamental architectural shift, integrating distinct functional modules beyond the linguistic core. It's about systemic integration, not just computational power. To address this architectural shift, our framework is guided by 3 critical research questions. First, what are the distinct functional blocks of an agentic system beyond its linguistic core? Second, how do these blocks interact to transform a reactive model into a proactive agent? Finally, what are the implications of this stratified architecture for responsible development and governance? These questions form the bedrock of our investigation. These guiding questions lead us directly to the Agentic Capability Stack, or ACS. The ACS is a conceptual framework that breaks down agentic architecture into 8 distinct interdependent capabilities. Each layer adds critical functionality, moving the system beyond the limitations of pure linguistic competence. The stack progresses logically, building from raw computation to autonomous and governed action, with each layer extending the capabilities of those below it. Next, we'll delve into each of these 8 layers in detail. The Agentic Capability Stack provides a comprehensive overview of the 8 distinct layers crucial for developing autonomous systems. Each layer builds upon the preceding one, creating a hierarchical structure for agentic architecture. This framework moves beyond simple linguistic competence, integrating capabilities from foundational computation to responsible action. We'll now delve into each of these layers individually, starting with the computational bedrock. Layer 1, parametric scaling, forms the computational foundation for all subsequent agentic capabilities. This layer represents the raw processing power and data encoding ability of modern AI systems. While essential, parametric scaling alone is insufficient for achieving true agency. It provides the necessary computational capacity, but higher-level architectural components are required to translate this power into autonomous action. This foundational layer sets the stage for connecting to external knowledge. Building on parametric scaling, Layer 2 introduces retrieval-augmented generation, or RAG. This capability addresses the inherent limitations of native LLMs, which are often constrained by static training data and prone to factual inaccuracies. RAG transforms the model from a closed system into an open one, enabling dynamic access to external databases and real-time information. This connection to external knowledge is crucial for informed decision-making and forms a prerequisite for structured thought processes. Layer 3, controllable reasoning, structures the thinking process, moving beyond the opaque end-to-end generation of standard LLMs. Frameworks like React explicitly interleave reasoning steps with actions, making the deliberative process transparent and auditable. This think-aloud approach enables debugging, guidance, and interpretability. Controllable reasoning is an absolute precondition for any form of strategic foresight, leading us directly into deliberative planning. Layer 4, deliberative planning, extends controllable reasoning by enabling the exploration of multiple future trajectories. Methodologies such as tree of thoughts allow the system to generate and evaluate various potential next steps, selecting the most promising path. This represents a significant leap from linear reasoning to strategic, goal-oriented planning. The efficiency of this planning is greatly enhanced by an understanding of potential consequences, which we will explore further with world models. Persistent memory is crucial for an agent to develop a continuous identity and learn from past interactions. Without it, each interaction is an isolated event, preventing cumulative experience. Architectures like generative agents introduce explicit memory modules to store observations and long-term plans. This allows the system to adapt its behavior based on accumulated experience. Memory also feeds into other layers, providing context for planning and enabling learning from feedback for alignment. This capability moves us beyond mere deliberation towards a system that truly evolves. Even with robust planning and memory, An agent remains limited without the ability to act. Tool use extends the agent's reach into the digital world. This layer enables the agent to interact with external systems through API calls, performing actions like searching the internet or executing code. Tool use relies heavily on effective planning, which dictates when and how to deploy specific tools. The results of these actions then feed back into the agent's context, often via RAG mechanisms, informing subsequent reasoning cycles. This is how an agent transitions from internal thought to external action. An advanced agent must not act blindly. It needs to understand the consequences of its actions. World models provide this crucial predictive capability. This layer involves the agent constructing an internal predictive representation of its environment. This internal model allows the agent to simulate potential outcomes before committing to an action, which is vital for long-term planning and risk management. Building a robust world model requires observing the results of tool use and generalizing these observations into predictive rules stored in memory. A strong world model significantly enhances planning efficiency. An autonomous and capable agent can be dangerous if its actions are not aligned with human intentions and values. Alignment and governance form the critical final layer, acting as a control and supervision framework. This layer incorporates mechanisms like reinforcement learning from human feedback to ensure actions remain within safe and beneficial boundaries. Governance requires visibility into all lower layers, monitoring reasoning, auditing memory and tool use, and constraining world models. This ensures that agent autonomy is always exercised responsibly and ethically. This is not a functional capacity, but a necessary oversight. The Agentic capability stack is not a mere collection of independent features, it's a deeply interconnected hierarchy. Each layer builds upon and extends the capabilities of those beneath it. Parametric scaling provides the foundational computational power. RAG requires a competent linguistic model. Controllable reasoning structures thought, which then enables deliberative planning. Persistent memory stores the complex data structures from lower layers. Tool use depends on planning decisions. World models are built from observing action results. Finally, alignment and governance must monitor and constrain all preceding layers. This hierarchical logic ensures a cohesive and functional agentic system. Having established the hierarchical logic of the ACS, we now turn to the rigorous methodology underpinning its development. This framework was built upon a systematic literature synthesis. Moving beyond simple reviews, we employed structured narrative synthesis combined with inductive thematic analysis. This approach allowed us to identify foundational works that introduced demonstrable new agentic capabilities. Our inclusion criteria were stringent, focusing on architectural contributions with empirical validation and significant community impact. This ensured the framework's grounding in robust, evidence-based research. Next, we will detail the thematic analysis process that transformed this literature into our conceptual framework. Following the systematic literature selection, our analytical process unfolded in 3 distinct stages. First, we applied rigorous inclusion criteria to select relevant literature. Then, we conducted a thematic analysis and inductive framework construction through open coding and functional grouping. This allowed themes to emerge directly from the data. Finally, we abstracted and hierarchized these themes into the 8 ACS layers. The hierarchization was not predetermined. It emerged inductively from analyzing logical dependencies. This iterative refinement ensured each layer's position reflects genuine architectural necessity, not arbitrary ordering. This systematic approach provides a robust foundation for the practical implications we will discuss next. Our rigorous methodology leads directly to significant practical implications, particularly for architectural design. The ACS framework offers concrete guidance for building truly autonomous systems. Organizations cannot achieve genuine agency through parametric scaling alone. Effective agentic systems demand deliberate integration of persistent memory, strategic planning, and controlled tool use. Crucially, governance mechanisms must be designed directly into the system architecture. This framework enables systematic evaluation of existing capabilities and identification of architectural gaps. It transforms agentic development from ad hoc engineering into principled design. This design focus naturally extends to how we validate these systems. Building on architectural design, the ACS framework also enables rigorous empirical validation of agentic systems. We can move beyond vague claims of intelligence or autonomy. Each layer of the stack can be independently tested and benchmarked. For example, parametric scaling is measured through standard language model evaluations. RAG effectiveness is assessed via knowledge retrieval accuracy. Reasoning quality is evaluated through interpretability metrics. Planning capability is tested through multi-step problem solving. Memory persistence is validated through long-horizon task performance. Tool use proficiency is measured through API call accuracy and appropriateness. World model quality is assessed through prediction accuracy. Alignment is evaluated through human feedback and safety metrics. This granular validation approach underscores the critical need for robust governance. The implications for governance and auditability are profound and non-negotiable. Our analysis reveals that while parametric scaling is necessary, it is fundamentally insufficient for robust, safe, and aligned agency. The emergence of genuine agency requires deliberate integration of persistent memory, strategic planning, controlled tool use, and crucially, governance mechanisms. For organizations adopting these technologies, the message is unambiguous. Auditability and technical governance are not optional. They are non-negotiable preconditions for responsible implementation. This includes immutable reasoning logs, tool access policies, human intervention protocols, and continuous alignment monitoring. This leads us to consider the organizational implementation strategy. Moving from theoretical understanding to practical application requires a structured approach. Organizations must implement agentic systems in a layered, incremental fashion. This means building a strong computational foundation first, then adding knowledge augmentation. We then layer on structured reasoning before attempting complex planning. This staged implementation ensures safety and auditability throughout the development process. This deliberate, step-by-step integration is crucial for responsible deployment. Our first future research direction focuses on operationalizing the agentic capability stack. We need to develop an agentic maturity model with quantitative metrics for each layer. This model will transform our framework into a powerful evaluation and benchmarking tool. It will enable rigorous comparison of different agentic architectures and help organizations identify specific capability gaps. This will provide objective assessment criteria for agentic systems. Next, we consider how to extend this framework to new domains. Our second future research direction extends the framework beyond digital agency. We must integrate sensory-motor and social interaction dimensions to cover the full spectrum of intelligence. This is essential for building agents that can operate effectively in physical environments. It requires incorporating perception, motor control, and social understanding into the framework. This expansion will enable the development of truly embodied autonomous systems. Now let's consider the most urgent research area. While extending to physical interaction is vital, the most pressing research area involves designing robust governance architectures. This isn't merely theoretical, it demands applied work on mechanisms like immutable reasoning logs. We need to develop concrete tool access policies and human intervention protocols. This research is absolutely critical for ensuring a safe and beneficial future for autonomous agentic systems. It's about building trust and control into the very fabric of these advanced systems. This leads us directly to our key takeaways. So, what are the core messages we want to emphasize from this discussion? First, the journey from a large language model to genuine artificial general intelligence is not an automatic process, it's a deliberate design challenge. The Agentic Capability Stack framework provides a clear roadmap for navigating this complex transition. It highlights that true agency emerges not from simply scaling up existing models, but from the systematic integration of 8 interdependent capabilities. Each layer adds crucial dimensions of autonomy, and critically, governance is not an afterthought. It's an architectural requirement, demanding comprehensive auditability and technical oversight from the outset. This framework guides us toward a responsible future. In conclusion, the Agentic Capability Stack offers a structured, actionable approach to understanding and building autonomous systems. By breaking down agency into these 8 distinct layers, we move beyond abstract concepts of intelligence. We focus instead on concrete, measurable, and manageable capabilities. The framework underscores that true autonomy demands not just raw computational power, but also persistent memory, structured reasoning, robust planning, controlled tool access, a deep understanding of the environment, and most importantly, strong governance. Organizations, researchers, and policymakers must embrace this framework. It's how we ensure the development of agentic systems remains aligned with human values and societal benefit.